Hello everyone, my name is Ariful Islam.
Hi everyone, I am Durga Acharya and we are going to present about our final project presentation about data visualization. And here is the presentation outline of our presentation. We are going to cover about the introduction, existing work, importance of visualization, investigation, objective data and method, and visualization method that we adopted, and the conclusion and future work of our study. And here we can see that the earthquake can happen by subducting plate like this moving, and it got energy stored in this, and when the energy get max out, that rock can bear and it get fractured and release the energy. That is the process of the overall earthquake. And the in existing visualization technique, we adopted like United States Geological Hazard Program visualization, and we analyzed the Japan visualization uh, image from the Japanese Meteorological Agency. And the importance of our visualization is that helps to understand about geophysical research, how the tectonic process and the fault behavior impacts by the earthquake, and it helps to helps for the seismic hazard assessment, and it helps to enhance the public safety because it visualizes more earthquake prone area and the less earthquake prone area. And
So,
the investigation and the objective, we focused on the subduction zone, and the subduction zone is from the Cascadia subduction zone, which is from the western part of the US and the Japan. And we focus on those subduction zone because these are the more earthquake prone area, and they have most powerful earthquake in the past time. And our objective is to analyze about the temporal trend and the spatial trend of the seismic activity in those regions, and it helps to understand by risk mapping based on the frequency, magnitude, and the distribution of the overall area. And how we made like visual representation that help to understand seismic data of that region.
so we'll use data sources from United States Geological Survey for both US West Coast and the Japan earthquakes. So we selected magnitude 2.5 as our cutoff magnitude, because we'll select all the magnitude be above this 2.5, and we select 20 years of data, 2 decades from 2000 to 2022 for temporal distribution analysis. So some of the this data comes as a comma separated value format or CSV format, and it includes a lot of information about the earthquake, but we mostly use the time of the earthquake for our geophysical analysis, also the location of the earthquake in terms of latitude, longitude, and depth and magnitude. There are some other auxiliary information such as the type of magnitude, number of stations that recorded the earthquake, the error, and so on. So after getting the data from the USGS catalog, we did some cleaning up so that we can load the data in pandas easily. So we handled the missing values, we corrected for some errors in the data and detected some outliers. So uh, uh, it was loaded into pandas without any error, and we could do the analysis. So we considered quite a few methods that we learned in this course to kind of like plot the earthquakes and see any patterns visible, and compare and contrast both Japan and Cascade subduction zone, so we can see the differences. So we considered box plot, histogram, cumulative plots, heat maps, and pair plots. We considered box plots so that we can see the distribution of average magnitudes in both study areas, which area generates more powerful earthquakes. Also histogram for the temporal distribution in both areas, heat map for identifying clusters of earthquake. We also tried some other methods such as the complex 3D plot, but we failed in that cases because although it showed us a lot of earthquakes, but we could not see any pattern in 3 dimension. So that's why we kind of discarded it, but it is still in our notebooks. So this is the first top maps, two maps plotted using hollow view shows us the locations of earthquakes. In the first image, we have west coast of United States, and here we have Japan. And we can visually see the dots representing earthquakes. We have a lot more earthquakes in 20 years in Japan compared to west coast of United States. So they are color coded based on their depth. The second map shows the density map of earthquakes. Here we can see in the left in Cascadia map, we have about three smaller clusters of earthquake, whereas in Japan we have a big cluster of earthquakes happening in the coastal region.
So in spatial distribution result, we also analyze the magnitude versus depth scatter plot. We can see that the Cascadia subduction zone earthquake are happening in between the 0 to 100 kilometer depth, and in Japan there is the shallow to deep earthquake like 500 to 600 kilometers. So it is the more strong earthquake and the deep earthquake area, and we can see that here the magnitude of the earthquake of the Japan, we can see that there is the most of the earthquake is happening between the 4.5. So these area have the strong earthquake than the Cascadia subduction zone. Here in Cascadia subduction zone, the most prominent earthquake is around the 2.8 magnitude. And we also compared the magnitude distribution of the two region. Here we can see that in Japan we have like higher magnitude, that is the 9 Richter scale magnitude, which is the Togo earthquake, and in the Cascadia subduction zone we can see like 2.8 magnitude, which is the mean value, and in the Japan the magnitude are the overly dispersed than the Cascadia subduction zone.
So here is the first of the plot on the top shows the temporal distribution of earthquake as a histogram. Here we can see in Japan, the number of earthquakes in each given bin is much higher than Cascadia, which is represented in this pink colored, and the bluish colored are represented by Japan. Here we can see around 2011, we have a big jump in number of earthquakes. This is caused by a magnitude 9 earthquake called Tohoku earthquake in 2011. This caused a lot of before shocks and smaller aftershocks. That's why we have a lot of earthquakes here. Also in the bottom, we have the cumulative number of earthquakes in both regions. So over the period of 20 years, we have about 100,000 earthquakes in Cascadia and about 200,000 earthquakes in Japan. So we have same period of time and same magnitude window. Within that time, we have twice as mass earthquake in Japan compared to Cascadia. We also have plotted the depth versus time in Japan and Cascadia in 20 years. So we can see if over time we see any change in the depth at which the earthquakes occurs. Here we can see the depths are all dispersed in all depths. So there is no change in depth of earthquake occurrence with time, but we can see that the maximum depth here as well in Cascadia is about 80 kilometers, whereas in Japan it goes up to 600 kilometers. So it's a very big difference in both areas. Also, we have magnitude versus time scatter plot. Here we can actually see a very concerning pattern in the data. We can see the magnitudes in Japan a little bit higher most of the time, but there is a straight line that looks artificial, and we think that this is error in the data that does not include these 3 to 4 magnitude data after 2009 in the USGS catalog. So it might be a problem in the USGS catalog, not in our plots. Also, cumulative energy, we can here see is a log plot of the energy released by each earthquake. So if we in joules, So in red in Cascadia, we can see if we compare both the energy released by both subduction zones, we can see about 1,000 times more energy is being has been released in Japan compared to Cascadia.
And in peer plot, we establish the relationship between the magnitude and the depth and the number of station and the gap between two station, and we can see that the Japan has the more station, and there is the more data in the Japan area, so we can establish a relationship between the each other. And in conclusion, we conclude that Japan has a border range and higher magnitude of earthquake than the Cascadia subduction zone, and the Japan earthquakes are the more dispersed than the Cascadia subduction zone, and also the temporal trend of the Japan has the higher energy release and the higher amount of the earthquake distributed over the time, and the Japan has the better seismic network. We can get a better accuracy than the Cascadia subduction zone.
So in future, we want to extend our analysis in more areas, like more other subduction zones, and we also want to include a large number years, or we want to expand the time for which we analyze. For example, here we are analyzing only for 20 years. We want to expand it to maybe 50 years or more. And we also want to develop maps that can show us the most earthquake prone areas in with higher resolution.